I know you just take that by yourself. What? You have to take it, right? Just put it in.
Can you guys see that?
Yes.
Okay, just making sure. Now, this is kind of following the outline, typing part of it, writing part of it, which always makes it more fun, but you know. I'll write it this way.
So are the notes meant to be displayed?
Yeah. Yeah, they were supposed to be. Okay, so what we're looking at, first of all, we had the notation. When you're trying to represent sets, you always use the curly braces. And you use X such that, and then this is usually a written sentence of some sort. So X such that some property holds. So if you're looking at this example right here, then if you're looking for the written set, this would be X such that X is in the naturals and X is odd and X is less than 14. It's written in some sort of sentence form for that part. That is the same thing as writing them with the listing. So you can either list it or give a description for it. If you give a description for it, you always use the colon right there, and you always put X colon. So you know what X is a variable, and then what the description is describing the variable. And then the description. Mm-hmm. Yep. The set of all integer multiples of 3, they write that using 3z, and you saw that in one of the proofs that you had to do for your outline. So 3z is just 3 times this z over here is just in our integers. That capital boldface z, it equals the integers. So that's just a set of everything in the integers. Now, a few more definitions, and then we'll get to a couple of proofs, and then we'll do homework. So let phi be the empty set. That's going to be defined to be the set that of all x, so that x is not equal to x. There's many different ways of trying to define the empty set. This is the one this book chooses to do. All x, so that x is not equal to itself. Well, that's an impossibility. So it's an empty set. Phi, it's a capital phi, P-H-I. Yep. It's the Greek letter phi. Phi is the empty set or the null set. Our notation, A is a subset of B, if and only if for every x in A, x is also in B. So this is read A is a subset. That's what that means. Do what, huh? They're strange. And they're going to give you a headache before you're done, because you're going to have true-false questions dealing with the empty set. Things like what we're going to find out is that the empty set is a subset of any set for every set A. The empty set's a subset of it. So then that raises a question, is the empty set a subset of this set? Now let's look at this set right here. This is a set with the empty set symbol in it. It is not the empty set. That's important. It's the set with the empty set symbol. That's not the empty set. But the empty set is a subset of every set. So it doesn't matter if I give you this set with the empty set symbol in it. The empty set is still a subset of it. Now, what is also true in this case is that the empty set is an element of that set. Element of means you have to see it written in that form in the set. Okay. Element of means it has to be written the way you see it in that set. Subset means that it's a group of elements in the set. You guys see the difference? You're going to have a headache before you're done with the homework because they're going to have true false questions about
It's
that.
only a face and the other one
Say that one more time?
like element of is just that is just one piece.
It's just one piece and it has to be written exactly the way you see it.
And the subset is just
It could be a whole bunch of them, or it could be one part of it. So, in other words, if you had the set 1, 2, I could write this one. This is a subset of the set 1, 2. But it's not an element because it has the braces around it. But it would be an element if I put it in the set and I put braces around it. So now it's an element. So for the element symbol to be correct, it has to be written exactly the way you see it written inside the set. If there's anything extras around it, all of that has to be part of what's inside the set for the element symbol to be correct. For the subset symbol to be correct, you have to be able to remove the braces and see those values inside the set. That's the difference. And that's a big difference. You're going to have true false questions. They're going to ask you about that. Okay, so definition 6. The set B is a proper subset if and only if B is a subset of A and A is not equal to B. That tells you that A has something extra in it. Something extra not in B. So there's something extra. Okay, let's look at the next one. Our definition for the direct proof of A contains B. You're going to start, your hypothesis is always going to be up to this line right here. Suppose X is in A. Let A be your set. Suppose X is in A. You have to be able to show that X is in B, and then this is our conclusion. So this is our hypothesis. This is our conclusion. This one we need to do. You have a homework problem like this. Let A and B be natural numbers, and let AZ and BZ be the sets of all integer multiples of A and B, respectively. Prove that if A divides B, then BZ is a subset of AZ. So this is going to be my scratch work. I'm going to type the proof up in a second. Well, a minute. What is AZ defined to be if I write it in set notation? Z is in, boldface Z. And BZ then is going to be the same thing, but it's going to be B little z. Z is in capital Z. And we want A and B are natural numbers. And then what else do we know? We're going to say A divides B. That's all our hypothesis. So why? That's our hypothesis. We have a lot of hypothesis for this one. So let's go through. If A divides B, what does that tell us about the relationship for A and B? Well, that's where we're headed. But just the divides definition. If A divides B, I know there exists an integer m such that B is equal to A times m. Right? There's our definition. And then we're trying to show that BZ is a subset of AZ. How do we show subsets? Element chasing. So we have to start with something in BZ. So what do we want in our BZ? Okay. Let X be in BZ and show X is in AZ. That's what we have to do to be able to show the subset. What does it mean for x to be in BZ? Yeah, so it has to be b times some z. We'll call it z1. And what does it mean for x to be in AZ? Yeah, except it's a different z, right? How do I get from BZ1 to AZ2? Well, how about I use that right there? B is equal to A times M. And so X would be equal to BZ1, which is AMZ1. But that's A times our Z2 if Z2 is MZ1. So it's substitution. Does that make sense? Okay, that's all my scratch work. That's everything I need to know to be able to write the proof. You have it written down enough for me to go type it up? Okay, so here's where we're going to be to type it up. Let's get our proof statement. The hypothesis, let A and B be natural numbers, and those are all the integer multiples of A and B respectively. And then we have one other part of our hypothesis. Let A divide B. So suppose that A divides B. What does that mean? We're going to go straight to our definition for divides. Yeah. B equals A times M for some integer M. Now, maybe we need to look at our, we're trying to start with something in BZ, right? So we're going to let X be in BZ, and I guess we can put it right here. It's going to, yeah, I'll just put it right here. What does it mean for X being BZ?
There exists an X such that,
There exists a Z, we call it Z1, in the integers such that X is equal to B Z1. By substitution, what do we know?
X equals A and Z1.
But that is equal to A times some Z2, where what would Z2 be equal to then? And that is an integer. What does that tell us? X is an AZ, right? Because it's A times something. That's how you get to be an AZ.
And also, B.
Also what, huh?
Also,
X started in BZ, yeah. I'm going to do one thing right here. I'm going to put these on display and write what they're equal to. Equal to BZ. BZ is in the integers. So here's the rule right here, and that's where it was. Question?
For like on some of the assignments or things that I'm asking, you said you want like numbered lines or?
On outlines only,
Oh, okay.
not on homework.
Okay.
And there's a difference. Let me take a moment to explain the difference. On outlines, I have two huge goals in this class, whether you learn anything else. The first one is, can you read a proof that someone else has written and understand exactly what's going on? The second one is, can you write a proof of some theorem statement someone gives you? I'm teaching you to read by having you do the outlines. I'm teaching you to write by having you do the homework. So there are two different points. On the outlines, you've got the proof, and you've got to tell me that you know what happened in the proof. Therefore, write it in a numbered list with each step that they do on its own line, and the reason why for each step that they do. On some of the proofs, they'll give you the reason why, and you just have to type it out. On other ones, you have to figure out what it is. You'll find this book is very good at not telling you what the whole hypothesis was. I still want to see that whole hypothesis, because we're at the point that it's still a struggle to identify what the hypothesis is. So I still want to see that you identify the hypothesis. And the conclusion also at the end. Did you know what you were trying to do? So that's why the difference. That's why we do the outlines. That's why we do the writing of the proofs. And why we take time in class to write proofs and do the homework. Okay, so now does this make it a little more clear why we said x was equal to bz1? If it's in here, it has to be in this form right here, that bz. That makes sense? And then if I say it's equal to some a times some other z, then that says it has to be in that set. So I'm going to put this right here. Therefore, x is in AZ. What is the conclusion then?
Since X is in AZ and X is in BZ.
Yeah, since x was arbitrary. What does it mean to be arbitrary? Yeah, there was nothing specific about it. It was just some element. So we started with some element in BZ, and we showed it lived in AZ. It follows that we're going to have AZ is a subset of BZ. So what's our final conclusion? We're going to copy and paste. How about that? So this is what we did. Therefore, if A divides B, then BZ is a subset of AZ. You have an equals in your homework assignment. That means you have to show set equality going both directions. Very similar proof, but it's not going to be identical. We're going to do that in a few minutes. Okay, so let's go back to our outline. On this one, did you guys understand the proof of part A and part B on this theorem? On part A, they said if x is in the empty set, which is false, then anything is true. So x element of the empty set is false, so false implies anything is true. That was from our logic part in the first chapter. So I know that part A has to be true because there's nothing in the empty set. Therefore, the empty set has to be a subset. Everything in the empty set's in A because there's nothing in the empty set. So it's all in A. Part B says A is a subset of A, and that one followed real easily because you said, okay, let X be in the first A. Then you know that X has to be in the second A. Therefore, the first A is a subset of the second A. They're just applying their subset proof. It just happens to be the same set, so it's really easy. But the part C one, for all sets A, B, and C, if A is a subset of B and B is a subset of C, then A is a subset of C. How would we show this? You're trying to show A is a subset of C. According to our direct proof method, what do we have to do to show A is a subset of C? Yeah. Let X be an arbitrary element in A. Show that X is an element of C. But what do you know? Yeah, A is a subset of B, tells you X has to be in B, because everything in A lives in B. That's what it means for A to be a subset of B. We also know that B is a subset of C, so that says X has to be in C. And then we're going to conclude. Does that make sense? So that one, I just have to go this way to get to it. That one is going to be, we're just going to prove part C right here. What's the hypothesis statement? Yeah, in fact, it's all of this. Yeah, for all sets A and B. And so we're going to let A, B, and C be sets in that part right there. So, let for all. Let there exist. Let A, B, and C be sets. Such that A is a subset of B and B is a subset of C. What is the rest of the hypothesis? Let X be an element of A. Let me turn that into a red element. Now apply what we know. Since A is a subset of B, I know that X has to be in B. Since B is a subset of C, I know that X has to be in C. Thus, since X in A was arbitrary, I know that A is a subset of C. Does that make sense? So how would you show equality then? If A equals B and B equals C, then A equals to C. Same way. There's no difference because, if A equals to B, then A is a subset of B. If B equals C, then B is a subset of C. So you're going to start with something in A, it has to live in B, and then that tells you it lives in C. So then that tells you A is a subset of C.
Would you really need to use subsets to prove that though?
Yeah, because we're using our definitions. This is a verification of what you want to claim is true. Yeah, so we actually do have to do it. So let's actually write this one up. Let A, B, and C, I did not want to do that, B, C, but it still did not work. I'm going to have A equals to B and B equals to C. To show that we have to show containment going both ways, to show A is contained in C, let X be in A. Then I know that A equals to B, so X has to be in B, right? Since B equals to C, yeah, it's spelled today. So I know that X has to be in C. Thus, since X was in A, it was arbitrary. I know that A is contained in C. Now, is there any difference from starting in C and going back the other direction? When the proof would be identical, other than exchanging the letters, we can do something to shorten it. It's called similarity. So I have containment going both directions. What does that tell me? Let's just see. And then we draw conclusions. Therefore, have something similar to that in your homework. The last one we need to just touch on here is going to be our power sets. What is our definition for our power sets? We already did that. The power set of A is a set of all elements that are whose subsets of A. So in other words, if we have the set X is going to be 1, 2, 3, 4, 5, and 6, the power set of X is going to be the set of all subsets of X. So notice that we have this element. It's a set. So I have to actually put braces around each element that I see in there. So that one has 2 sets of braces because it already had 1 set of braces. And then we have to put braces around the next one, 4 and 5. And then braces around the 6. And that's all the single ones. And now we're going to group them together. So the first one, 1, 2, 3, 4, 5. And then the first and the third. And then the second and the third. And then all of them together. Got enough braces? Yeah, everything in the set has to get braces around it. So that's the first time. And then you group them by pairs of 2 and put braces around it. And then you group them all 3 together and put braces around it. So yeah, there's a lot of things for that power set. It does take forever to do when you're typing it up. Okay, so how would we do this one? Let A and B be sets. Then A is a subset of B if and only if the power set of A is a subset of the power set of B. What is the hypothesis? Yeah, A and B are sets. And yeah, now we have to go forward. And the forward is going to have a baby hypothesis. A is a subset of B. And then the backward is going to have a baby hypothesis. The power set of A is a subset of the power set of B. You're smiling at me.
Yeah, let me baby hypothesis.
Baby, yeah. They're little ones. They're inside. Okay. So if A is a subset of B, I know that everything in A lives in B. And I'm trying to show that the power set of A is a subset of the power set of B. So we also have to add to it. And X is going to be an element of the power set of A. Well, what are the elements of our power set of A? Well, subsets of A. Yeah. So if X is an element of the power set of A, then X has to be a subset of A. But A is a subset of B. So then that tells you X is a subset of B. So it has to be in the power set of B, which is a set of all subsets of B. Yeah. Now going back the other way, we have to add something to our hypothesis. What is that going to be? X is an element of A, yes. So if X is an element of A, what do I know? A has to be a subset of the power set of A. Because A is a subset of itself. Sorry, A has to be an element of the power set of A. I'm going to get element and subset mixed up with these. I always do. A is an element of the power set of A. It's a subset of itself. So then what does that tell you about this X right here? X is in a subset in the power set of A. Now, where does this A live if we know the power set of A is a subset of the power set of B? If A is an element in here, and this is a subset of this right here, then A is actually an element of PB. Remember, the power sets is sets of sets. A is in the power set of A. Power set of A is a subset of a power set of B. So everything in power set of A is in the power set of B. So A is in the power set of B. But what do I know then if A is in the power set of B? Has to be a subset of B. That's our definition of the power set. But if A is a subset of B, well, then we're done. I actually don't need to know that X is in A. I just actually proved it directly from the power sets. Does that make sense? This one's typed up in the book, so I'm not going to worry about typing this one up. What we're going to do is homework. Now we have about 15 minutes, so let me tell you which homework problem was the hard one. That's the one we're going to do in class. Number 13, that's your hard one. 9 and 13 are proofs. The other ones are true and false, or writing things using power set notation. I'm sorry, using set notation. So 9 and 13 are your proofs. So go ahead and work on 9 and 13.